Okay. Yeah. Good morning to all. I hope. Can you hear me? My voice is clear for you? Okay. What about my voice? Is it clear? Just let me know that. Okay. Fine, fine. Yeah. Yes, yes. Yeah, good evening. Vikrant, good evening. Yes, good evening to all. Fine. Then coming to yesterday, we just started our synchronous machines, and we have seen what is the importance of synchronous generator over the induction generator. Because as you know, synchronous generator, most of the power generation is by synchronous generator. The reason is, the main reason is it can generate both active power and also reactive power. It can generate complex power, active power and also reactive power. Because most of the loads are required active power, reactive power. Reactive power is mainly for the produce the magnetic field. Because magnetic field is the medium through which power conversion takes place. No? Without magnetic field, there is no power conversion. Right? Yes. But induction generator or induction motor, magnetic field is provided by the reactive power. Whereas in our synchronous generator, we are providing the magnetic field by DC excitation that we are going to see. Okay. And also the advantages of synchronous generator, their power factor can be controlled and it can be operated at good power factor. So good efficiency. Fine. So that's the reason synchronous generators, most of the power generation is by synchronous generators. Okay. And also we have seen the advantages of and why to have frequency, standardization of frequency, what is a why to have constant frequency, right? And the problems with the low frequency, problems with high frequency. So frequency will be standardized as 50 to 60 Hz frequency. Also with 50 to 60 Hz frequency, steam power plant is good efficiency. Good efficiency, that is also one factor we have discussed. Okay. And we just started that principle of alternator. The alternator works on the principle of Faraday's law of electromagnetic induction. So according to Faraday, whenever flux linkages changes in a coil, an EMF will be induced in that coil. Okay. But flux linkages in our practical machines, how flux linkages can be created? Flux linkages can be created by two ways. One is either by relative time variation or by relative space variation. Okay. A relative time variation means it is statically induced EMF. No relative motion is required. But whereas relative space variation means that is in all rotating machines, dynamically induced EMF by relative the space variations. Okay. Yeah. Now let us continue the same. I'm sharing the whiteboard. Okay. Yeah. Just we are continuing that principle of alternator. Continuation of principle of alternator. Yesterday I have taken a conductor, a set of magnetic poles. Let us continue with the same. Just for your reference, this is a pole. The north pole and this is south pole. Okay. North pole and south pole. The flux direction is from north to south. And I will quickly revise this. Of course, we have discussed this topic, but for continuation, I need it. So the flux is from north to south pole to south pole. If you take a conductor, this is a conductor. The conductor is driven, or it will be moved in upwards direction. When conductor is moving in upwards direction, in the flux density B, its angle is theta. Therefore, induced EMF is equal to E is equal to BLV sin theta. In a single conductor, E is equal to BLV sin theta, magnitude of induced EMF. And no derivation is required. As I told yesterday, yes. Only you may expect a problem on this. Thing is, you should know the relation, but units must be proper. B will be Webers per meter square, L is in meters, V meters per second. The direction of induced EMF. The direction of induced EMF can be found by applying the Fleming's right hand rule. Fleming's right hand rule or flat form rule. In this diagram, forefinger flux direction, thumb motion of the conductor. This is the direction of the current. Okay. So, as I told yesterday, forefinger must be kept along the flux direction. Thumb must be movement of the conductor, but your center finger must be always along the conductor. So, flux direction, motion of the conductor. This is the current direction. This is the current direction by applying the Fleming's right hand rule. So, the direction of induced EMF or direction of induced current is in this direction. It is a cross, na? Yes. E or I is a cross. Current is going away from the observer. Okay. But in practical cases, practical alternator, conductor, it will never move upwards or downwards direction. It is not upwards or downwards direction. It is not in the form of a single conductor in practical machines. Always the conductor will be in the form of coil. It is not in the form of a conductor. And there will be multi-turn coils. And that multi-turn coils will be kept in the rotor core, or you can also keep on the stator core. So conductor in practical machine, the conductor will be in the form of coil. There is no single conductor. They will be in the form of coils. Of course, they may be multi-turn coils. And they will rotate. They rotate. Here I have showing upwards or downwards, but practical cases, the coil will rotate. Armature conductors will rotate. They will rotate. So to show this, let me take a coil instead of a single conductor. This we have discussed yesterday, right? Now, instead of taking a single conductor, let me take a coil. So with that, I would like to come to some important conclusions. Okay. Let me take a coil. I will move to the next page. This is already there. See. This is the North Pole and this is South Pole. Flux is from north to south. So let me take a single turn coil. A single turn coil. So this is a flux direction. Let me take a coil. This is a coil. It will be connected with a resistive load across the coil. EMF will be induced in this coil, na? Yes. And the coil is rotating in. This is rotating in upwards direction, and this is moving in downwards direction. So that coil is said to be rotating in clockwise direction. Correct? This coil is said to be rotating in clockwise direction. Coil is rotating in clockwise direction. So therefore, one side of the conductor is moving upwards direction, other side of the conductor is moving downwards direction. This is a single turn coil. Single turn coil. For example, say this is A and this is B, C and D. AB is one conductor and CD is another conductor. So it is forming a coil. ABCD is a single turn coil. So AB is one conductor, CD is another conductor. But AB is moving upwards direction, CD is moving downwards direction. So that coil will rotate in clockwise direction. Correct? Tangential direction you have to take. When coil is rotating, when one AB is under the north pole, this is under the south pole, it is moving upwards, downwards. So it is rotating. For this, apply your right hand rule. What is the direction of induced EMF? Apply your right hand rule. Okay. See. Four-finger flux direction, thumb motion of the conductor. Current is A to B. Current is A to B. Or else you can apply flat form rule. Flat form rule. Four fingers are placed along the conductor. Thumb is upwards. But flux should enter perpendicular to the palm. The palm is always opposite to north pole. So the current is in this direction. A to B. Direction of the current is A to B. A to B. This is in this direction. Cross. Whereas in CD, it is moving downwards direction. Yes. So apply your flat form rule. The palm should be always opposite to north pole. Flux center here, but it is moving downwards. Then what is the current? Current is towards the observer. It is coming towards me. Then dot. This dot. Okay. If current is going away from the observer, means arrow. You're getting? When current is away from the observer, means it will be cross. When current is coming towards the observer, I can feel it is like a dot. Whereas it is going this side, I can feel like a cross. Like a cross. This is a dot. Yeah. So in this coil AB, the direction of the current is A to B. Here it is C to D. If you connect a load here, for example, I am connecting a resistive load, say. A load is connected, R is connected across the coil. Then path for the current. The path for the current is A to B. It is passing A to B and B to C, C to D. C to D to the load in this load. So it is complete the path. A to B, C to D. Right? But in conductor AB it is cross, conductor CD, the induced EMF is dot. So why? Because it is, I will ask you a question for you. Can you tell me why induced EMF in conductor AB cross, why it is in conductor CD dot? It is because of direction of flux changes or direction of motion of conductor. Under north pole AB cross, south pole CD dot. Why the direction of the current is reversed? It is because of a flux direction is reversed or motion of the conductor is different. Motion of the conductor, because one is moving downwards, one is moving upwards. flux is always north to south only, north to south, flux direction same. But conductor, it is moving upwards, it is moving downwards. Both together rotating in clockwise only. Upwards means this is cross, downwards means it is dot. Okay. Whenever this conductor AB is there, na? When conductor AB under north pole cross, but while it is coming under the south pole, it is again conductor AB is going to be dot. CD will be cross. When conductor is rotating, right now I am showing under north pole cross. While it is coming under the south pole, it will be dot again. Reason is common sense is under north pole it is moving upwards direction, tangentially moving upwards direction. While it is coming under the south pole, it will move downwards direction. So conductor AB cross, while it is going under the south pole, it is going to be dot. And a current reversal takes place. When conductor north pole positive half cycle, say when it is coming under the south pole, negative half cycle. Similarly, other side of the conductor also, other side of the coil also. So the EMF is not same. Direction of induced EMF is not same in the same conductor. It will alternatively changes. Okay. Important point here is what I want to say. Conductor can be represented with a voltage source. Conductor can be represented with a voltage source. What is the practical voltage source? Practical voltage source is alternator, not battery. Battery is it is a charged one. Active voltage source. Active voltage source is a alternator. But in alternator, where EMF is induced? In conductor. Whenever conductor cut the flux, EMF is induced in the conductor. Therefore, conductor I can show with a voltage source. So therefore, here, this is conductor. I can show like this. And other side of the conductor, this is minus and plus. The coil, no? Yes, minus and plus. This is moving upwards and this is moving downwards. The polarities are plus minus, minus plus. I am fixing the polarities. Fixing the polarities. Or instead of taking, if you don't want to take it is plus and minus, how we can take? Let us show. I can show like this. AC voltage source. It is not DC voltage source, na? It is AC voltage source. We can show like this. AC will also have polarities, na? AC also will have polarities. Yes. AC positive half cycle plus minus A. Negative half cycle it is minus plus, na? Yes. But whatever it may be, minus plus, reason is the current is delivered from the positive terminal. Here also current is delivered from the positive terminal. When current is coming out from the positive terminal, act as a generator. If current is received from the positive terminal, act as a motor. If current is coming towards the positive terminal, it acts as a motor. It is absorbing the electrical energy. But whereas current is delivered from the positive terminal, generator. Here both are generating, na? Yes, these are the polarities. Current is leaving from the positive terminal. Here also current is leaving from the positive terminal. Based on that, I am deciding the polarities, plus minus, minus plus. For example, if this is 10 volts in this conductor, 10 volts in this conductor, what is the net voltage? Net voltage across the coil, 20 volts. 20 volts. It means induced EMF in two sides of the coil at any instant, they are said to be aiding. The induced EMF in two coils are said to be aiding polarities. Aiding polarities. If it is a full pitched coil, say it is arithmetic sum. Just arithmetic sum. That this concept is required at the time of full pitch winding and short pitch winding. So the conclusion is the induced EMF in two sides of the coil. The induced EMFs in two sides of the coil. In two sides of the coil will be aiding polarities. Will be aiding polarities. That's said to be aiding polarities. Aiding. Of course, 10 volts, 10 volts, 20 volts. Fine. But practical cases, it is never be a single coil. A coil will be multi-turn coil. More number of turns will be there. Here I have taken only one coil, na? Yes. But it will have more number of turns. So let me add another turn for this diagram. This is single turn is there, na? One more turn I am adding. This is the two-turn coil, and this is the three-turn coil. Three-turn or four-turn coils. It is a multi-turn coil always, practically. More number of turns means more EMF. The voltages are said to be aiding, na? Yes. More each conductor you are showing with a 10 voltage source, right? Now 3 turns are there, definitely voltage will be 3 times. 3 times. Induced EMF is proportional to number of turns. If more turns are there, EMF is more. Correct? Yes. EMF is proportional to number of turns. E proportional to number of turns. More turns are there, more EMF. Because all voltages are said to be aiding polarities. Right? Okay. Now, this coil actually kept in the rotor, but the induced EMF is said to be AC. Induced EMF is AC. A, B, C, D, well, they are changing. So, EMF is going to be changes. And how frequently EMF reversal takes place? That is nothing but frequency. It is generating AC, na? AC important property, frequency. First of all, what is the frequency? Frequency is nothing but how frequently the EMF reversal takes place. How frequently the current reversal takes place. How many cycles per second? How many cycles per second? Okay. So now let us see frequency, expression for frequency, frequency of generation. Frequency. Expression for derivation of frequency. That is F is equal to Pn by 120. How many cycles there depends on the number of poles and also frequency. F is equal to Pn by 120. Let P is the number of poles. That P is the number of poles. P is the number of poles. N is the speed in RPM. Speed in RPM. And F is the frequency in cycles per second. Frequency in cycles per second or hertz. Or hertz. Cycles per second or hertz. Frequency, cycles per second. So first let me take, for easy understanding purpose, 2 poles I will take. Only 2 poles. 2 poles. Two poles. North pole and south pole. See, this is north and south. Flux is from north to south. I am taking now front view, the diagram. This is the flux direction. Flux is from north to south. And this rotor is rotating in clockwise direction. Okay, yes. And I would like to take only one conductor, single conductor, say. The same thing also valid for coils also. For easy understanding purpose, I would like to take a single conductor. Single conductor. With the prime mover, we are rotating in clockwise direction. We are rotating in clockwise direction with a speed of n RPM. It is driven with speed of n RPM. Okay. So, yeah. Poles are stationary. Conductor is rotating. Conductor is kept on the rotor. Now, when it is rotating, in which direction this conductor will rotate? Here, the conductor will move in this direction. At this instant, it will move in this direction. Then what is induced EMF? The induced EMF is said to be 0. It is not cutting the flux. When conductor is in between the poles, it is not cutting the flux. Induced EMF is 0. Say for example, this is instant 1. At instant 1, what is induced EMF? Induced EMF is 0. It is not cutting any flux because simply it is moving parallel to the flux lines. No? Flux is from north to south, whatever it may be. It is moving in this or in this. Sin 0, 0, sin 180 also 0. I am taking this as a reference. It is not cutting any flux, simply moving parallel to the flux lines. But after some rotation, the conductor is moving like this. No? Conductor is moving. It will come to here. Conductor will come to here. The same conductor only coming to here. Right? Came to here. Now, how it is moving? It is moving perpendicular to the flux lines. Perpendicular to the flux lines. Therefore, maximum flux cutting. Right? Conductor is moving perpendicular. Maximum flux cutting. So, at instant to 2, I can say, this is at instant to 2. EMF is maximum. EMF is maximum as conductor is moving perpendicular. What is the polarity of that? Or induced EMF? Cross is the flux direction, motion of the conductor. Current is inwards. Inwards. Current is inwards. Cross, na? Yes. It is a cross. Cross. Because current is inwards. My diagram I am taking. So conductor is said to be perpendicular to the board. Okay, machine is like this I am taking. This machine is circular shape I am keeping. Vertically machine is kept. If you see from top view, how you can feel it is like a circle. Actually machine is circular shape. It is, we are keeping like this. I am seeing conductor can be kept like this. So flux direction, motion of the conductor. Motion of the conductor, flux. Current is inwards, inwards, cross. Inwards. That is maximum. And again after another 90 degrees, the conductor will come to here. Conductor will come to here and it is moving like this. Moving like this. Okay, are you getting? So here, conductor always moves tangential direction I am taking. Tangential means, for example, see, if you take 4 conductors, 4 conductor here. If this is rotating in clockwise direction, how this conductor will move? Downwards. This conductor will move in this direction. This conductor will move like this. This conductor will move like this. Tangential we have to take. Our 3 fingers are mutually perpendicular. 3 fingers mutually perpendicular means, so you have to take a direction of motion of conductor straight. In other words, tangent. Of course, here I am taking 4 conductors, but in the example, whatever I am showing here, that is single conductor, only one conductor only, that is rotating. And the rotor it is kept, while rotor is rotating, conductor rotate. For easy understanding purpose, one conductor I am taking. Okay. In other conductors are there, both EMF still aids, that's all. Here 10 volts is a, if you connect one coil, it may be 20. Forget about magnitude. Okay. Then what is EMF at this condition? At instant 3 say. Induced EMF is again 0. It is simply moving parallel to the flux lines. It is not cutting, moving parallel to the flux lines. Another after 180 degrees, say. Another after 90 degrees, it is coming to here. It is coming here. Okay. It is moving downwards. Moving downwards. Then again it is cutting 90 degrees. Induced EMF is maximum. Induced EMF is maximum, but what is that? It is dot. At instant 4, EMF is maximum. EMF is maximum. Moving perpendicular. But flux direction, motion of the conductor. Current is outwards, na? Conductor is outward. Current is outwards. Flux direction, motion of the conductor outwards. Is a dot. It is coming out from the board, out from the paper. Outwards, you can say. EMF is maximum. And again, coming to here, the induced EMF will be 0. So same conductor, I have driven with a 360 degrees. For every 90 degrees, you are observing. The induced EMF will be here 0, here maximum, here 0, again here maximum. Therefore, see, if you draw that, the induced EMF waveform with respect to E, with respect to angle, see here at instant 1 and at instant 2, instant 2, instant 3, instant 4, and instant 1 again, 1 to 1. I am coming 1 to 1 for 360 degrees. 1 to 1. At 1, induced EMF is 0. Instant 1, induced EMF is 0. But after 90 degrees, instant 2 means after 90 degrees, again induced EMF is maximum. Instant 2. But at instant 3, again EMF is 0 because conductor is moving parallel. Whereas induced EMF 4, induced EMF is maximum. Again maximum. Of course it is dot. Conductor is moving perpendicular to the flux lines. At instant 1, again 0, 0. If you join all these things, it is AC. It is alternating voltage. In a single conductor, whatever we have observed, when conductor is under the north pole, induced EMF is positive half cycle. When conductor is going under the south pole, it will be negative half cycle. Negative half cycle. This is cross. Correct? But of course, it is due to which pole? North pole. This is due to north pole. This is due to south pole. The north pole it is cross. Under south pole it will be dot. It is dot. Okay? It is dot. Fine. But I am taking only direct 4 instants. 0 position, maximum position I am taking. At instant 1, 0. At instant 2, maximum after 90 degrees. Instant 0 it is not cutting. 1 is not cutting. After some time it may be cut 30, sin 30. Sin 60 increases. Sin 90, maximum. Like that. So, observation here is, simply I can say, when conductor is going under the north pole, generate positive half cycle, while going south pole, generate negative half cycle. So if two poles are there, it will generate 2 half cycles. Or can I say simply, each pole generate 1 half cycle. Each pole, when conductor is rotating, each pole generate 1 half cycle. 2 pole machine, within 1 rotation, 2. If you take 4 pole machine, what will happen? 4 pole machine say, under north pole positive half cycle, south pole negative half cycle, north pole positive half cycle, south pole negative half cycle. EMF reversal takes place. Under north pole crosses say when coming south pole dot. The 4 pole machine means 4 times EMF reversal takes place. 4 poles are there. Within 1 rotation, the conductor will undergo all the poles. 4 times EMF reversal takes place. 4 half cycles you will get. 4 pole machine. If it is a 6 pole machine, 6 half cycles you will get. 6 half cycles. P pole machine, P half cycles, P half cycles. So simply each pole, I can write like this, each pole generate one half cycle. General case, each pole generate one half cycle. North pole generate positive, south pole generate negative half cycle. One half cycle. For a P pole machine, say, for a P pole machine, P number of poles we have taken. For a P pole machine, for one rotation, how many half cycles it will generate? P half cycles. P pole machine, P half cycles. Or that is equal to P by 2 full cycles. P by 2 full cycles. P half cycles for P pole machine, P by 2 full cycles. If you take for N rotations, per minute, no? N rotations per minute is equal to how much? That will be P by 2 into N. P by 2 into N cycles per minute. Cycles per minute. Why cycles per minute? Because rotations per minute. Within one rotation, P half cycles, P by 2 full cycles, na? Yes. Within one rotation. But N rotations means P by 2 into N. But that is per minute or per second. N is rotations per minute. Therefore, within that P by 2 into N cycles per minute. Because N is minute. Cycles per minute is not hertz. It must be converted into cycles per second. Hertz means cycles per second. That's the reason what we will do. P by 2 into N by 60. Cycles per second. Cycles per second. That is itself hertz. Or they are also called hertz. So Pn by 120. Pn by 120. Therefore, frequency is equal to Pn by 120. So F. Therefore, F is equal to Pn by 120. Where N is in RPM. I have taken N is in RPM. Pn by 120. Cycles per second. For example, if now I will ask a question. N is taken RPS, say. For example, N is given RPS. Here you see, in this diagram, here N I have taken N rotations per minute. Dear students, see, N rotations per minute. That's the reason P by 2 into N cycles per minute. Because speed is per minute and this is also in minute. Cycles per minute that we are converting. Pn by 120 cycles per second. But if it is N rotations per second is given, what is going to happen? N rotations per second means P by 2 into N cycles per second. That is itself hertz. Speed is per second means rotation per second. No need to convert that into divided by 60 is not required. Minute kabatti, since as it is minute, divided in 60 to get the cycles per second. If N is given RPS, then it is going to be simply F is equal to Pn by F is equal to Pn by 2. Pn by 2. Pn by 2. If N is given in RPS. RPS. Okay. Yeah. So frequencies depends upon what? Number of poles and speed. Pn by 120 say. Number of poles and speed. If more poles are there, more half cycles you will get. Correct. 4 poles are there, 4 half cycles. 6 poles are there, 6 half cycles or 3 full cycles. 100 poles are there, say 50 cycles you will get. 100 half cycles and 50. So definitely more cycles for, if more poles are there, more cycles. So frequency is more. If rotating high speed, say, for 1 second it is rotating 10 rotations, say, definitely cycles will be multiplied with 10. Fastly rotating, EMF reversal. How fast the rotating conductor will go, that much faster under North Pole, South Pole, North Pole, faster going means EMF reversal takes place. Yeah. Pn by 120, Pn by 2. But being the students, don't expect questions on this relation in GATE examination. But even the students will do the mistake here also. For example, I will give one question. See, the question is a three-phase, an alternator with 20 poles, or a four-pole alternator running at a speed of 25 RPS. Now the frequency of induced EMF. Frequency of induced EMF is A bit 25 hertz, B bit 50 hertz, right? And C bit 0.83 hertz, D bit 1.25 hertz. 1.25 hertz. Right? Then what is the frequency? Four-pole machine rotating at a speed of 25 RPS. 25 RPS means F is equal to Pn by 2, na? F is equal to Pn by 2. It's a four-pole. N is 25 by 2. How much it will be? 50 hertz. So your answer is 50 hertz. Instead of that, if you use F is equal to Pn by 120, say Pn by 120, what is going to be happen? That is 4 into 25 divided by 120. If you give, you will get 0.83 hertz. 0.83 hertz. But you will also give that answer also. You will give that option also. That option also you will give. But which is totally wrong, na? The step is totally wrong. No. What I mean to say from this example, options definitely, you will give all varieties of options. There is a choice of doing mistake. Generally, students, they can remember F is equal to Pn by 120, Pn by 120. Whether N is given RPM or RPS, we cannot observe. Simply you substitute F is equal to Pn by 120, right? Pn by 120, 0.83 you will get. That also will be given. Okay. Definitely 100 students are there. At least one student will do the mistake or not. Definitely. But that's such type of silly mistakes should not be. Okay. Don't expect this type of questions in GATE examination. At the same time, don't neglect the silly mistakes. Okay. This is expression for frequency. Now, observe from the earlier diagram. I want to make some important conclusions from the earlier diagram. See here. From the earlier diagram. Yeah. This is said to be direct axis. What is this? This is called direct axis. I am using another color, green color I am using. This is called polar axis. Polar axis or direct axis. Polar axis or D axis. That is nothing but D axis. Center of the pole, D axis. This is said to be interpolar axis. Interpolar axis. Interpolar axis, or it is said to be Q axis. Q axis. Polar axis is nothing but center of the pole, along the pole. Quadrature axis in between the pole. Interpolar axis in between the poles. Important observation. When conductor is existing under the pole, the center of the pole, EMF is maximum cross maximum dot. EMF is maximum, na? Yes. EMF is maximum. When conductor is under the pole, EMF maximum. But when conductor is in between the poles, center of the pole, EMF is zero. Okay, when conductor is existing along the quadrature axis, EMF is zero. Direct axis EMF is maximum. Direct axis EMF is maximum. Remember that. This is valid everywhere. Everywhere. When conductor is under the pole, along the direct axis EMF maximum. Because the common sense is when conductor is existing center of the pole, under the pole, whether it may be moving clockwise or counterclockwise, it will cut the flux by 90 degrees. It cut the flux by 90 degrees. Right? Yes. But when conductor is along the quadrature axis, okay, it is rotating like this. Along the quadrature axis, it moves parallel. So therefore, my statement is when conductor is along the direct axis or conductor is under the pole, EMF is maximum. But when conductor is along the quadrature axis or in between the poles, EMF will be zero. Under the pole, between the poles. So the statement is, listen. The induced EMF in the conductor. When the conductor is existing, when the conductor exists along the direct axis, along the direct axis or polar axis, along the direct axis, or that is under the poles, under the poles. When conductor exists along the D axis or under the pole, the EMF will be, the induced EMF will be maximum. Induced EMF will be maximum. Whereas when conductor exists, along the D axis, along the Q axis, the interpolar axis, along the Q axis, or that is in between the poles, in between the poles. In between the poles. Between the poles, the induced EMF will be minimum, or that is zero. Induced EMF will be zero. Induced EMF is zero. This statement is valid throughout our alternator. Not only alternator, every machine it is same. When conductor under the pole, definitely it will move perpendicular only. Whether clockwise or counterclockwise, pole is like this. Flux is coming, na? It moves perpendicular only. But in between the poles, move parallel to the flux. Okay. Yeah. Right. Okay. So up to now, I have taken a single conductor or a coil and it is driven in clockwise direction. But a conductor is rotating or coil is rotating. Coil is rotating. But in our practical machine, the coil can be conductor that we are going to call armature. That can be kept on the stator also. Stator and poles will rotate. Earlier we have taken the poles stationary, conductor is rotating. But what I am going to take next step, conductor is kept on the stator, poles can rotate. Then also flux cutting. Then also flux cutting action, then also induced EMF. Their only thing is relative motion must be exist. To exist the relative motion, conductor is stationary. To exist the relative motion, conductor is stationary, poles are rotating. Or poles are stationary, conductor is rotating. Both is valid. So let me take now stationary conductor. Stationary conductor, rotating magnetic field. And that to be, I want to take three-phase alternator. Three-phase alternator. Okay. Three-phase alternators are very common. No? See. This is rotating armature or rotating conductor. Taking rotating conductor. Conductor can also be called as what? Armature. Not rotating, sorry, stationary. Stationary armature, rotating magnetic field. Stationary armature or conductor. Stationary conductor, you can call armature. Conductor only armature. And rotating field. Rotating field. Field is nothing but poles. Field is itself poles. Poles. When poles rotate, there only field rotate. Where poles are there, flux will be there only. Na? When poles are rotating, flux will rotate. Because flux is produced by the poles. For this, okay. This is stator. These are the poles. Salient poles. Salient poles. On this, we are keeping DC excitation. They are excited with DC. Excite with DC. And it is driven in clockwise direction. This is driven in clockwise direction by using the prime mover. Prime mover. And keep the winding R phase, Y phase, B phase. Say this is R phase, this is Y phase and B phase. See, this is R phase winding, Y phase winding and B phase winding. B phase winding. Taken? Yes. Now we are coming towards our practical generator. Yeah, take down fastly. Right. Stator. I'm showing only front view, no? Front view. Actually, how the generator, how the three-phase alternator means, it will be like this. If you take actually, sorry. Yeah. See, it will be like this. This is the stator core. Stator core like this, na? Yes. There are three phases I am taking, R phase, Y phase, B phase. But how they can be kept in the slots, na? Their slots will be there. So in that we will keep the conductor. In that we will keep the conductor, R phase, Y phase, B phase. Of course, so many coils will be there. Just for example, I am taking only one conductor for R phase. But at least one coil must be there. Like so many coils, they will be distributed. So to begin with, I am taking only one conductor. So if you see front view, how it looks like a circle, na? A circle. And pole is also, how pole will be, pole is going to be like this. This will be the pole that we are going to salient pole. We are going to call it a salient pole. It will be like this. It is like this. And they are excited with DC. And all these things we are going to see at the time of construction very clearly. We will see. They are excited with DC. But this much diagram instead of drawing, I am drawing left side. Okay, I am drawing the left side. Simple diagram. This isometric view we will see at the time of construction of alternator. Okay. Front view we are seeing. Front view which looks like a circle and 3 conductors I am taking. Now based on the current direction, I am giving DC excitation, field current. When field current is given, based on the current direction, tell me this act as a north pole, na? North pole. This act as south pole. I think you will be knowing thumb rule. Transformers already completed, na? Thumb rule. Or at least BTech are completed. What thumb rule says? The fingers indicates current direction, thumb indicates flux. Fingers indicates current direction, thumb indicates flux. Okay? Yes. So this is a pole, say this is a pole. Coils are kept like this and they are wound up. It is giving the flux. It is giving the flux means act as a north pole. Who is giving the flux? It is acting as a north pole. Flux direction is in this direction. Yes, this is giving the flux. This is giving the flux. So which is giving, that is acting as a north pole. Other one is acting as a south pole. And the flux direction is like this. This is the flux direction. Flux will take a return path. Flux will take a return path and reaches to the south pole. Reaches to the south pole. North pole is giving the flux. Flux is taking return path. South pole is receiving. South pole is receiving the flux. So this is the flux direction in the air gap. This is a flux. Okay. Yeah. But what is the flux direction inside of the magnet? Inside of the magnet is south to north. Outside of the magnet, north to south. Now, you don't worry about it is inside or outside. Air gap, what is the flux? The flux direction in the air gap is important. Air gap. Air gap means gap between stator and rotor. So this is the flux direction. This is our flux direction. Flux direction. Of course, it is not going outside of the core. In the air gap, flux is coming, it is taking return path through the stator core. So between the stator and rotor, flux is in this upwards direction. Upwards direction, it is taking return path. So just for direction, I'm writing outside flux. If you rotate this rotor, now rotate the rotor in clockwise direction. I am rotating with the prime mover. The prime mover torque is in clockwise direction. So it is rotating in clockwise direction. Clockwise direction. Now tell me, what is induced EMF in the R phase? The induced EMF in the R phase. Is it cross or dot? The induced EMF can be found by applying the right hand rule. Right hand rule. Okay. But what right hand rule says? According to right hand rule, 4-finger flux direction, 4-finger we know. Thumb motion of the conductor. Thumb motion of the conductor. But is the conductor is moving? The conductor is not moving here. Conductor is stationary. Conductor is kept on the stator. Poles are rotating. Poles are rotating in which direction? This pole is moving in clockwise direction. Poles are moving in clockwise direction. Rotor is moving in clockwise. But according to our right hand rule, 4-finger flux direction, thumb motion of the conductor. Thumb should be motion of the conductor. But we know flux direction. Thumb is not moving. Na? Thumb in the sense conductor is not moving. Thumb shows motion of the conductor, but conductor is not moving. Therefore, in which direction you can keep your thumb? Conductor is not moving. So without knowing this thumb, you cannot find current direction. Thumb direction must be known. But conductor is not moving, therefore thumb we cannot assume. So therefore what you have to do? You need to assume direction of motion of conductor. Though conductor is not rotating, right? To find the direction of induced EMF, I can take, this is the rotor field rotation. Field rotation is in clockwise direction. Yes, tangential I am taking. This is the field rotation. Field rotation is in clockwise direction. Then conductor direction of motion of conductor, you have to assume in opposite direction. Assume this will be the motion of the conductor. Direction of motion of conductor, you need to assume. Direction of motion of conductor. Actually, it is not moving, but we need to assume in this direction, opposite to the field rotation. We need to assume opposite to field rotation. Opposite to field. Why? Because if this is field is rotating in clockwise direction, say field is rotating in clockwise. If conductor also rotating in clockwise, what will happen? What is the relative motion? If field is rotating some 1500 RPM, conductor also rotating 1500 RPM. What is the relative speed? 0. Relative speed is 0. You are assuming conductor also same direction, say relative motion is 0, no induced EMF. But is there any relative motion or not? Relative motion is there. Conductor is stationary, poles are rotating. Flux cutting takes place. Flux cutting is take place. EMF is induced. Relative motion is not 0. Therefore, don't assume in this direction, in the same direction. So when conductor is stationary, you have to assume motion of the conductor in opposite to the field rotation. Opposite you have to assume. This is conductor rotation is correct. You have to assume in opposite direction. That is correct. Okay. So remember that when conductor is stationary, assume direction of motion of conductor opposite to the field rotation. Let me write that. If the conductor is stationary, when the conductor is stationary, assume the direction of motion of conductor, assume the direction of motion of conductor in opposite direction that of field rotation. Opposite direction that of field rotation. Field is rotating clockwise. I am assuming it is counterclockwise. Counterclockwise and tangential, no? It is moving counterclockwise means at this instant in this. Poles are moving in clockwise. Tangential. Conductor is stationary. Assume motion of conductor in opposite direction. Yeah. Then tell me current direction. Current in the R phase. Let me apply. 4-finger flux direction. Now taken this. Now I am coming. 4-finger flux direction. Thumb motion of the conductor. Then current is inwards. Current is inwards. Into the board, into the paper, inwards, cross. That is cross. In this it is cross. But at this instant, if you draw the induced EMF in these conductors, right now in this conductor, induced EMF is maximum or minimum? Right now in the R phase, induced EMF is maximum. Induced EMF is maximum in the R phase because the R phase is under the north pole. It is cutting maximum flux. So induced EMF is maximum. And when south pole is coming, induced EMF is maximum negative. Dot will come. Yes, south pole is coming dot. So if you draw that, the waveform, R phase voltage. So this is R phase, this is R phase. And if you take this is Y phase, Y yellow phase. And this is B phase, B say. R, Y, B. So how R phase voltage waveform? This is R phase voltage waveform. R phase. Then right now here, slowly rotor is rotating. Okay. Let me write clearly. Positive half cycle under north pole, negative half cycle under south pole. Okay. And when north pole is rotated 120 degrees, what will happen? When north pole is rotated 120 degrees, north pole will comes under the Y phase. then maximum value of induced EMF will be after 120 degrees. Are you getting my point? Right now you are at north pole. No? This is conductor. This conductor is there. Where it is there? Under R phase. So first north pole cutting the R phase. Induced EMF is maximum in the R phase. After 120 degrees, this north pole is coming under the Y phase. Then it will cut the Y phase. Y phase. Induced EMF is maximum in the Y phase after 120 degrees of R phase. After 120 degrees. And similarly, so now it is north pole is here under the Y phase. Another 120 degrees, it will comes under the B phase. Now it cuts the B phase. Cuts the B phase, induced EMF is maximum. Right? Yes. So here you can see highlighter. North pole is here. After 120 degrees, north pole will come to here. Cut the Y phase. Then induced EMF is maximum. Another 120 degrees, it will cut the B phase. Induced EMF is maximum. And now my point is the maximum value of R phase is there. After 120 degrees, maximum value of Y phase takes place. Another 120 degrees, maximum value of B phase takes place. So if you draw that, the waveform for Y phase, and B phase, see RYB. Yeah. So this is Y. Y phase will be like this. And B phase will be like this. This is a B phase. And Y phase. Y phase. So RYB, na? Yes. This is induced EMF in the R phase, but this is in the induced EMF in Y phase, EY, but this is induced EMF in the B phase, B phase. Okay. And what is the phase sequence? Phase sequence is RYB. RYB means first R is coming, next Y is coming, next B is coming. So phase sequence for this is RYB phase sequence. This is RYB phase sequence. This is a phase sequence. This is omega t, na? Yes, this is omega t. Time angle or omega t. So first R phase is coming. Maximum value of R phase 2, maximum value of Y phase 120, maximum value of B phase 120. B phase 120. So first maximum R phase, next maximum value in Y phase, next maximum value is in B phase. Phase sequence is RYB. Now, if rotor is driven in counterclockwise, what will happen? Tell me. If rotor is driven in counterclockwise, rotor rotated in counterclockwise, what will be the phase sequence? First R will come. After 120 degrees, B will come. After 120 degrees, it is moving in this direction, B will come. After another 120 degrees, Y will come. So what is the phase sequence? RBY. This waveform is for clockwise. Counterclockwise ante here R, here Y will come. Here B will come. No, examiner, you want to ask a question. One diagram he will give, right? Options A, B, C, D will be given in the form of waveform. This diagram for this rotation, which is the waveform. Okay, for counterclockwise direction, which is the waveform. Whatever the waveform I am drawing for clockwise direction, because first it is under north pole, next Y phase, next B phase. North pole is under the, it is going RYB direction. Important thing here is induced EMF is said to be balanced. This induced EMF is said to be balanced because what is the maximum value of R phase to maximum value of Y phase? It is 120 degrees. And here is also maximum value of Y phase to maximum value of B phase is also 120 degrees. Their maximum values displaced with a phase angle of 120. They mean to say, if winding is spatially displaced, R phase to Y phase 120, Y phase to B phase 120. That's the reason maximum value of R phase to Y phase after 120 degrees, Y to B, balanced EMF. When you are getting balanced EMF, when winding is balanced, when winding is spatially displaced, spatially means on the stator periphery, if R phase is here, Y phase you keep after 120 degrees, then only peak value of R to Y will be 120. When winding is balanced, then induced EMF also balanced. Getting my point? Or else, say, I will take like this. Instead of keeping this conductor here, dear students, tell me if I keep Y phase after 90 degrees. Y phase after 90 degrees. Is this waveform valid? No, this waveform is not valid. Because space displacement R to by 90 degrees means maximum value of R phase after that Y phase maximum value will be after 90 degrees only, not 120, 90 degrees. And Y to B will be, it is a 150 degrees you will get, 150 degrees. Are you get this balanced EMF? No, I want balanced voltage means 120 degrees. When it is possible, the winding must be kept only at 120 degrees apart. 120 degrees apart means when winding is spatially displaced 120, then induced EMF will be facially displaced 120. The winding is balanced, induced EMF is balanced. Let me write that conclusion. When the winding is spatially displaced, when the winding is spatially displaced by 120 degrees, then the induced EMF facially displaced. Induced EMF will facially displaced, facially or timely, timely displaced by 120 degrees. Winding is space displaced, then induced EMF is facially or timely displaced. In other words, when the winding is balanced, when the winding is spatially balanced, then the induced EMF will be, facially balanced. So the generated EMF phase angles are depends on your winding placement. Winding placements. Okay. Yes. Right. Just for your information, if this is winding is kept like this, say R phase is here. North pole, south pole. R phase is here and Y phase is here, B phase is here. From here to here, if you keep 90 degrees, this is R phase, Y phase, B phase, 90 degrees. Say. How your EMF waveform? This is R phase, say. And one will be not 120. It will be only after 90 degrees only you will get maximum value will be 90 degrees you will get. 90 degrees you will get like this. One waveform. Another will be you will get after 270 degrees. This is going to be like this. Okay. Another will be from this to this, it will be 90 only. 90 it will be. From here to here, it is 90 degrees. But from here to here, it will be 150 degrees, not 120. Okay, but this is not preferred, no? It's not preferred. We do not prefer this type of voltage. (150°). So we don't want this type of waveform. Winding must be balanced. Okay. Yeah. Now coming to important point is the induced EMF is for earlier diagram. E1 is equal to induced EMF E1. E1 ER is equal to EM sin omega t. EM sin omega t. EY is equal to EM sin omega t minus 120. EB is equal to EM sin omega t minus 240°. Minus 240°. In the earlier diagram, our balanced alternator. Both are 120° space displacement. And if you draw the phasors for that, this will be ER, okay, ER, and this is EY, and this is EB. These may be phase voltages I am taking. Phase voltages ER. Phase voltage. But what will be the line voltage? Line voltage. So this is phase voltage, say. Line voltage is equal to ERY. Line voltage is nothing but it is ERY, na? Yes, ERY. ERY is equal to between phases, ERY. That is equal to ER minus EY. ER minus EY. So ER minus EY means line voltage. So it will be like this. This is minus EY. This is minus EY. Minus EY. Now resultant is, this is the resultant EMF. Minus EY, the resultant EMF. This is line voltage, EL, line voltage. Line voltage. This angle is 60°, no? Angle between these two, it is 60°. 60°. Now, line voltage is equal to, if I want to find line voltage, E line is equal to line voltage. E line is equal to square root of, this is A vector and this is another one is B vector. A vector, B vector. What is that? EL is equal to, this is also EPH. So that is equal to EPH square plus EPH square plus 2. Are you getting? Let me write here first. ER square plus EY square and 2 phasors. If I take EY 120 means instead of taking resultant of both A vector, B vector, A square plus B square plus 2AB, that is equal to EPH square plus EPH square plus 2BH square cos alpha, where alpha is the angle between both. That is a line voltage, line. So that is equal to 2 EPH square plus 2 EPH square cos alpha. So which is equal to EPH square. This is cos 60, no? cos 60 is equal to 2 EPH square plus cos 60 means simply it is EPH square. Cos 60 1 by 2. That is equal to 3 EPH square. That is equal to how much? Root 3 EPH. Therefore, line voltage is equal to root 3 EPH. Line voltage is equal to root 3 EPH. Root 3 EPH. And the phasors are rotating in counterclockwise direction. Phasors are rotating in counterclockwise direction. Then only ER0, EY minus 120. Then what about line voltage? Line voltage leads the phase voltage by 30 degrees. Correct? It is 30 degrees. I am taking here R phase voltage is reference. R phase reference. So important point is the line voltage EL leads, line voltage leads the phase voltage EPH by 30 degrees. Line voltage leads the phase voltage by 30 degrees. Okay. Line voltage leads the phase voltage by 30 degrees. Three-phase machine. Yeah. This is about three-phase alternator. Now let us take two-phase alternator. There are three types of alternators: single-phase alternators, two-phase, and three-phase alternators also there. Three-phase alternators. Let me take three-phase. No, three-phase we have covered. Two-phase alternator. For two-phase, is over now? Okay. Yeah. Three-phase alternate, two-phase alternator. Two-phase alternator. For two-phase alternator, the two phases can be kept at 90 degrees apart. Yeah. So here two phases. This is phase 1, 1 dash, 2 and 2 dash. Phase 1, 1 dash, 2 and 2 dash. One coil I am taking for each phase. Phase 1, 1 dash, phase 2, 2 dash, 2 dash. For this given direction, this is north pole, south pole, north and south pole. It is driven in clockwise direction. The rotor will be driven in clockwise direction. We are rotating this in clockwise direction. Prime mover rotating in clockwise. Right now tell me, in which phase maximum value of induced EMF takes place? Phase 1. Right now the conductor is under the north pole. So EMF is maximum in the phase 1. Phase 1. If you draw the waveform, the phase 1 is like this. This is the phase 1. Phase 1. Just a minute. Omega t. So phase 1 is, this is a phase 1. Induced EMF in 1 dash. And since rotor is rotating in clockwise direction, then induced EMF in the second phase will be after 90 degrees of phase 1. Phase 1 maximum, na? After 90 degrees, north pole will comes under the second phase. So induced EMF in the second phase will be maximum after 90 degrees. After 90 degrees. So it is like this. The induced EMF waveform so this is E2 and 2 dash. E2 2 dash 1 dash, but they will be displaced with an angle of 90 degrees. Both are displaced with an angle of 90 degrees. Peak value of phase 1 to phase 2 will be 90 degrees. Okay. So if you write E is equal to Em sin omega t, say sin omega t, then what is E11 dash? This is E11 dash. E11 dash is Em sin omega t. What is E22 dash? Em, E maximum sin omega t minus 90 degrees. 90 degrees. Both are displaced with an angle of 90 degrees because two-phase machine will be displaced with 90. If you draw this E11 dash, but E22 dash will be here. E22 dash will be here. 90 degrees they are displaced. And vectors are assumed to be rotating in counterclockwise. Vectors are, I am taking phasor rotation always in counterclockwise direction. Then only E22 dash will lags. E22 dash lags the E11 dash by 90 degrees. If you want to find the line voltage is 1 dash, E11 dash, E22 dash. But what is the line voltage? Line voltage is nothing but, of course, this is phase voltage. Line voltage is equal to E11 dash and minus E22 dash. E line is equal to E11 dash minus E22 dash. This is the line voltage, na? Yes, line voltage. Therefore, 22 dash I will take in opposite direction. This is minus E22 dash, 22 dash. Then what is the line voltage? See, line voltage will be this. This will be the line voltage, EL. And that EL is equal to magnitude of EL. EL is equal to how much? EL is equal to square root of EPH square plus EPH square. That is equal to root 2 into EPH. So in two-phase machine, line voltage is equal to root 2 times of phase voltage. Root 2 times. Okay. You need to calculate all these values. EMF equation ante not only one equation. You will give two-phase machine. What is the phase voltage? What is the line voltage? Dear students, just a minute. Why I am explaining all these things means just a minute. Listen, stop writing. Why I am explaining means options will be given in the form of waveforms. Options will be given in the form of numericals. Options also will be given in the form of equation, EMF equation, or simply the waveform. E11 dash is equal to E sin omega t. E22 dash for this it is sin omega t minus 90 only. Na? Options how you will get for this given diagram for clockwise rotation. A bit induced EMF in 1 dash, Em sin omega t, 2 dash, Em sin omega t minus 90. A bit, B bit Em sin omega t, Em sin omega t plus 90, say plus 90, like that. But it will be omega t minus 90. And induced EMF in first phase and second phase lags. because first maximum value is coming under the first conductor. Next north pole is coming under the second phase after 90 degrees. After 90 degrees. After until lagging. Correct or not? This is the time axis now. X-axis, time axis. First maximum value is in R phase. First maximum value is in 1 dash. Second maximum value is in 2 dash. And the second phase lags by 90 degrees. Okay. Yeah. If this E22 dash, if it is leading, say it is going to be wrong. 2 dash if you draw. So for example, instead of 2 dash like this, if I start from here, is it 2 dash? No. Can I say it is 2 dash? No, wrong. Instead of this one, you may be given, that is wrong. Okay. For this is correct. Yeah. Important conclusion here is this line voltage leads. This line voltage leads the phase voltage by how much angle? This leads by 30 degrees. Sorry, 45 degrees. EL leads. Important conclusion is EL leads EPH by 90 degrees. EL leads EPH by 45 degrees. In two-phase machine, 45 degrees. In two-phase. Three-phase, line voltage leads phase voltage by 30 degrees. 30 degrees. Now, if I want to write the equation here, line voltage equation, √2 into E maximum, sin omega t plus 45 I will write. Plus 45. Correct or not? E line voltage here, for the same thing, if I want to write all equation, E line is equal to √2 into E maximum, sin omega t plus 45 I will write. That is the equation. Sin omega t plus 45. Okay. Based on the diagram, questions also can be given. That's the reason I am explaining all these things. Okay. Yeah. Now let me give some questions based on the application of right hand rule. Okay. Let me give the question. I will give with GATE 2005 examination for 2 marks. See, question, GATE 2005 examination for 2 marks. Question is like this. Question is, two magnetic poles are revolving. Two magnetic poles are revolving around stationary armature. Stationary armature carrying 2 coils. Two magnetic poles are revolving around stationary armature carrying 2 coils. As shown in figure. Then identify the correct statement. Regarding the polarity of induced EMF. Induced EMF. and diagram is given. Is the diagram. Okay, yes. The North Pole, South Pole, these are the conductors, coils. C1, C1 dash, C2, C2 dash. And it is carrying two coils, C1, C1 dash, C1, C1 dash, and C2, C2 dash. C2, C2 dash, as shown in figure. Okay, I'm also writing coils as shown in figure. Two magnetic poles are revolving around a stationary armature carrying two coils, C1, C1 dash, C2, C2 dash, as shown in figure. Identify the correct statement regarding the polarity of induced EMF. And poles are rotating in clockwise direction. The poles rotation also given in clockwise direction. Now options are, options A bit, dot in C1, no EMF in C2. No EMF in C2. B bit, cross in C1, no EMF in C2. No EMF in C2. C bit, dot in C2, no EMF in C1. D bit, cross in C2, no EMF in C1. No EMF in C1. What is your answer? C1, C1 dash, C2, C2 dash. Question is clear now? Two magnetic poles, at a North Pole, South Pole, revolving around stationary armature. The circle is there, na? Is a core stator. It is not rotating. Don't think the circular shape, but the conductors are kept in that. It is not rotating. Circular shape, okay, not rotating. Simply it is fixed. But poles are rotating outside. Poles rotating outside. Conductors are said to be stationary. The circle part is stationary, not rotating. Poles rotating outside. The conductors are stationary, poles are rotating. What is EMF? Tell me. What is the EMF? Any one of you? What is your answer for this? Option? Option A, option B. Yeah, option A, option B, option A, option B. Okay, let us see. Listen, when conductor is, yeah. This question is clear now. I'm moving to the next page. Next page. Once again, I'm drawing the diagram. These are the poles. North Pole, South Pole. Correct? Yes. The North Pole and South Pole. This is one conductor, is one conductor, one conductor, one conductor. C1, C1 dash. C2, C2 dash. But poles are rotating in clockwise. What is the flux direction? Flux is always from north to south. The flux is from north to south. We need to understand this is the flux direction. Flux direction. Poles are rotating clockwise, then conductor is said to be rotating in counterclockwise direction. You need to take, for example, pole is moving tangentially downwards. When pole is moving tangentially downwards, I can take these conductors are said to be counterclockwise, upwards. When poles are clockwise means which direction rotor is assumed to be rotating in counterclockwise direction. This is a rotor rotation you have to assume. Actually it is not moving, conductor is not moving. Armature is stationary armature, not moving, but you have to assume. Assume means which direction this conductor is moving. It is said to be moving upwards direction. It is said to be moving downwards direction. That is our assumption. This is moving in this direction. This is moving in this direction. Okay. Tangential, na? As I told already, when conductors are there, if they are moving in counterclockwise direction, how they will move? It moves upwards. This moves downwards. It moves in this direction. Moves in this direction. Therefore, what is EMF in C2 and C2 dash? C2, C2 dash is 0. They are not cutting any flux. EMF, already we have given, this is direct axis, quadrature axis. No EMF in C2. No EMF in C2, C2 dash. As they exist along Q axis. Therefore, they are moving parallel. Parallel to flux lines. Therefore, no EMF. No cutting, no flux. No cutting, no EMF. There is no EMF in C2 and C2 dash. But EMF, that is induced EMF is maximum in C1 and C1 dash. EMF is maximum. E is maximum in C1 and C1 dash. E is maximum C1, C1 dash. Because they are moving perpendicular, na? Perpendicular. Since moving perpendicular. They are moving perpendicular. Maximum. Now find the direction of induced EMF. We know that flux direction. This is the flux direction. Flux. Flux is in this direction. This is the flux direction. Motion of the conductor is assumed. It is not moving, assume. This is motion of conductor, assume. They are assuming in counterclockwise direction, not moving actually. Then apply your right hand rule. Is the flux direction, no? Flux. Okay. Is the flux direction, motion of the conductor upwards, flux. Current is outwards. Is in this direction. Flux direction. Current is outwards. A dot in C1. But cross in C1 dash. Dot in C1. So, dot in C1, but no EMF in C1, no EMF in C2. Therefore, what is answer? Answer is A. A is your answer. Of course, not this much discussion is not required. Directly, I am giving very clearly. Okay, after some time I am not going to write anything. Directly you can keep your fingers in. I know flux direction. So poles moving clockwise, conductor is counterclockwise. You have to assume counterclockwise. They are stationary. Counterclockwise means C1 moves upwards. So flux, current is outwards. Okay. Similarly, next question. Let me give another question. This you have taken, na? Yeah. Next question is, let me give one question. This is SPDCL 2012 examination. 2012. the poles North pole, South pole, okay. Poles are moving clockwise direction, but these are the conductors. These conductors are kept in these slots. This conductor 1, conductor 2, conductor 3, conductor 4. Now the EMFs, the induced EMF in the conductors, the conductors 1, 2, 3 and 4 respectively, A bit dot cross 0, 0, B bit cross dot 0, 0, C bit 0, 0 cross dot D bit 0, 0 dot cross. Yeah, tell me what is the answer for this? Okay, induced EMF in the conductors 1, 2, 3 and 4 respectively. SPDCL, Southern Power Distribution Corporation Limited. I want to take for each model one question. Yeah, tell me what is the answer? What is the answer? Yes. Some of you are saying B, some of you are A. How can it is possible? Two options cannot exist now? Very simply I can say, what is EMF in 3 and 4? 3 and 4 will be 0, na? Induced EMF in 3 and 4, they are along the quadrature axis, they are not cutting any flux right now. After 90 degrees of rotation, then 3 and 4 maximum. But at that instant, you have to say. So you have to respond options based on the diagram. Right now, North pole is under the coil 1, conductor 1 and 2. Na? Yes, North pole cutting maximum under North pole. And second conductor under South pole. Therefore, for this diagram, EMF is maximum in 1 and 2. No EMF, 3 and 4, 0. But at the same time, this will be cross now. Yes, this is cross. Already we have seen this diagram. This is dot. Okay. Sorry. Yeah. What is in this? Answer will be B. Answer is B. Correct? B. You can directly keep flux direction upwards. Pole is moving clockwise, but conductor is assumed to be in counterclockwise direction. You need to assume. Assume counterclockwise. Correct? Yeah. So this is the flux direction. If I take only one conductor, say, it's under North pole, how it will be? This is the flux direction. If I take this is the flux direction. Which direction you have to assume? In this direction. This conductor number 1. In this. This is B, flux density. This is B. Okay. So this is a flux direction. Motion of the conductor. You have to assume. What will be the current? It is cross. Inwards. Answer is B. Clear? This is only first diagram I have taken already. This is the flux direction. Pole is moving. Conductor is stationary. You have to assume conductor is counterclockwise. Flux direction, you know, motion of the conductor. Current is inwards. Okay. Yeah, let me give another question. It's over now. Another question. Yeah. So here it is. Winding is kept on the poles. Winding is kept on the poles. Okay. These are the conductors. But on this pole, see, this is cross. This is cross. This is dot. This is cross. This is dot. And rotor rotation is in counterclockwise direction. Rotor is rotating in counterclockwise direction. This is a rotor rotation. Rotor rotation. Then EMF in A and B. EMF in A and B. EMF in A dash, B dash. Tell me, A cross or dot? In A cross or dot? B cross or dot? Yeah. So for this, what is going to be happen? Flux direction, you need to find the poles. Poles are said to be thumb rule, na? Thumb rule. Current is entering, current is leaving. This is a question. For this question, this is cross, this is dot. Act as a which pole? North pole, na? North pole. Current entering, leaving, north pole. And this is cross dot. It acts as a south pole. South pole. These are the conductors. But flux direction, this is the flux direction. Flux direction. And the conductors are moving. No need to assume they are moving. They are moving in counterclockwise direction only. Moving counterclockwise direction. Therefore, what is the flux direction? What is the motion of the conductor? Downwards, upwards. A and B. So therefore, flux direction downwards. Current is dot. This is dot here, and here it is cross. Dot and cross. Therefore, in A cross B dot. A cross B dot. A cross and B dot. Only thing is here, student is having idea to find the polarity of the pole. Polarity of the pole can be found by applying thumb rule, na? Thumb rule. Current is entering, current is leaving. North pole, current is entering. At the cross entering, it is leaving. Correct. This side cross, this side that means current is entering inwards, current is leaving. This is giving the flux. Flux is in this direction. North pole. For this current entering, leaving, it is receiving the flux. Okay. Yeah. Now, see. Next, another case. So far, we have taken two cases. Not two cases. What is that? When conductor is rotating, no assumption is required. When conductor is stationary, you need to assume opposite direction. Opposite. Third case is when both are rotating, what will happen? Both are rotating. Let me give induced EMF. You can say there will be four cases that exist. Four cases. See, number one, case one is, what is that case one? Case one is when conductor is rotating. When conductor is rotating, no assumption is required. No assumption is required. Case 2. Case 2. When conductor is stationary. When conductor is stationary, assume it will rotate. Conductor will rotate in opposite direction. Conductor has to rotate. Conductor will rotate in opposite direction that of field rotation. Opposite direction that of field rotation. Opposite direction that of field rotation. And coming to case 3, dear students, coming to case 3, when both conductor and flux is rotating, what is going to happen? Earlier, one stationary, one rotating. Case 3, when both conductor and flux, conductor is rotating and flux is rotating. Flux are pole rotating. How to apply our right hand rule, that I want to explain. For that, let me give you a question first. Question is like this. See, this is north pole. See, this is north pole and conductor is rotating. North pole is rotating at 1500 RPM. Conductor is rotating at 1400 RPM. 1400 RPM. AC. Similarly, this is north pole. Conductor is rotating 1500 RPM. And this is 1600 RPM. Then what is A? EMF in A. EMF in A is dot or cross. EMF in A is dot or cross. Dot or cross. Dot or cross. What is EMF in A? First diagram, tell me. First diagram. First diagram. But here I have taken third case is when both conductor is rotating and flux is rotating in same direction. Dear student, in same direction you add it. Same direction. Next time I am going to take in opposite direction. Same direction. So when both conductor and flux is rotating, flux means pole rotating, flux also will rotate, na? Yes. When both are rotating in same direction, when conductor is slower, you have to assume in opposite direction. Opposite direction that of field rotation or opposite direction that of original rotation. The first diagram, conductor is rotating clockwise, but we have to assume in counterclockwise because it is slower. Whereas in second diagram, conductor is faster, both rotating, conductor is faster. Then no assumption is required. No assumption is required. Let me write that conclusion is when both conductor and flux is rotating, flux are pole rotating in same direction, if the conductor is slower than the flux, or pole, then assume direction of motion of conductor in opposite direction that of field rotation. opposite direction of field rotation. And if conductor is faster, if the conductor is faster, the conductor is faster, then no assumption is required. No assumption is required. No assumption is required. Okay? Yes. No assumption. Therefore, see, I am coming back to the question. See, this is North Pole conductor. It is 1500 RPM. It is 1400 RPM means we know the flux direction already, but you need to assume, this is assume in this direction. Assume counterclockwise. Actually, it is clockwise, but you need to assume counterclockwise. And we know flux direction. This is the flux direction. This is the flux. Flux. Now apply our right hand rule. What is going to happen? Flux direction, motion of the conductor. Flux, motion of the conductor. Current is inwards. Inwards. The current will be inwards. Cross. Here it is cross. Therefore, EMF in A is cross in this first diagram, cross. Whereas in second one, it is 1500, it is rotating in 1600. So no assumption is required. No assumption. You know flux direction. This is the flux direction. Flux. No assumption is required. Therefore, what is EMF? Flux direction, motion of the conductor. Okay. This is a flux. Flux direction, motion of the conductor. Current is outwards. Outwards. Here, no need, no assumption is required in this diagram. No assumption is required. But earlier, you have to assume in counterclockwise direction. First diagram, because conductor is slower, you have to assume. So EMF in A is dot in this. Can you tell me, dear students, can you tell me where this case occurs? Where this case takes place? Induction machine, induction generator, induction motor. In induction motor, rotor conductor rotate less than synchronous speed, both same direction only. Induction motor, stator field synchronous speed, stator poles are stator field rotated synchronous speed, but rotor conductor rotate less than synchronous speed. Correct? Stator poles 1500 say, rotor is rotating some 1450 RPM less than. Whereas in induction generator, if you take induction generator, poles rotating at 15, rotor conductor rotate more than synchronous speed, both same direction. Right? Why I am saying these things? Because a damper winding is there now in our synchronous machine. Damper winding works on the principle of induction. Principle of induction. When rotor speed is more than synchronous speed, induction generator action. Less than synchronous speed, induction motor action. In the damper winding. There, this knowledge is required. Now, last case is case 4. Case 4. Conductor and field or pole rotate in opposite direction. Opposite direction. Both rotate in opposite direction. tell me what is the answer for this. North pole is rotating 1500 rpm. It is rotating 1400 rpm. Similarly, North pole. This is 1500 rpm. This is 1600 rpm. A. So EMF in A dash, EMF in A dash, A dash. Yeah, what is the answer? Anyone? What is the answer in first case and second case? First case and second case. Cross. Exactly correct. Very good. In both cases, cross only. Cross only. Because when conductor and flux rotating in opposite direction, whether conductor may be slower or faster, no assumption is required. No assumption is required. Because relative motion already increasing order. Relative motion is increasing order. So the thing is, if both conductor and flux are pole rotating in opposite direction, okay. No assumption is required. Whether conductor may be slower or faster, no assumption is required. Whether the conductor may be slower or faster, no assumption is required. No assumption is required. No assumption is required. Okay. No assumption. Relative motion already increasing order. Then apply your right hand rule. So in both cases, cross only, na? Flux direction, motion of the conductor, cross. Here also it is cross. Here also it is cross. Okay. Yeah. And where this case takes place? Induction motor or synchronous machine, everywhere. Negative sequence field. Rotor is rotating clockwise. Conductor is rotating clockwise. Negative sequence field may rotate in counterclockwise direction. Negative sequence field. Correct? Negative sequence field at a fifth harmonic field. It will rotate opposite direction that of rotor rotation. If the harmonic poles rotate opposite direction that of conductor, say. So any case, so whatever it may be, what will happen, if, as long as if there is relative motion is there, induced EMF takes place. Correct or not? Yes. Both may be same direction or opposite direction. Therefore, we have taken 4 cases. These 4 cases only exist entire electrical engineering. If you have idea about these 4 cases, no other rule is required. Fleming's right hand rule is enough. And all these 4 cases you have to see. When conductor is rotating, no assumption is required. Case 1. Second case, when conductor is stationary, you need to assume opposite direction. And when conductor is both are rotating in the same direction, conductor is slower, you have to assume opposite direction. Conductor is faster, no assumption. Fourth case is when both are rotating in the same direction, whether conductor may be slower or faster, no assumption is required. These are only the cases that will exist. Right? Yeah. So with this, these are the very basic things. Maybe most of you people may be knowing But at the time of coming to our actual synchronous machine, I cannot explain all these things. So for that, I am making you people ready to have about all these 4 cases, all these things, right? So, and next what we are going to see is important discussion, that is phase sequence of 3-phase alternator, phase sequence. Based on the phase sequence, so many questions you can expect. And you should have clear idea about the phase sequence. But today, so I think you can able to hear sound. Vinayaka Nimajjanam is going on in this colony. Vinayaka Nimajjanam. I also planned the same thing. So I want to take up to the first break, and after that class is not possible. So this is coming towards my house, and in this colony, so we cannot able to continue the class. Okay. So please bear with me. And tomorrow class will be same. Tomorrow class schedule will be same. Right? Tomorrow class will be class timings. Same. 5:30 to 9 or 9:30. Generally, I will take 5 to 9. That will be enough. 5 to, it may be 9:30 or 9. 5:30 onwards, let me write. 5:30 p.m. onwards. Okay. So now I will close here. Any doubts are there, please you can ask. Any doubts are there, you please ask. And after that, we will leave today, because the sound I cannot concentrate. Another important topic from here onwards, phase sequence, etc. Yeah. Okay. Shravan Kumar. Hello, Shravan Kumar.
Yes, sir.
Yes, please.
Good evening, sir.
Good evening.
Sir, one question, sir. SPDCL question.
SPDCL?
Yes, sir. Third question, sir.
Yes. This is SPDCL. Yes. Tell me.
No, sir. Next question.
Next question. This one?
Yes, sir.
Sir,
how you assumed your north and south, sir? Because dot and cross poles are same.
I have not assumed, but we need to find. For example, see here, a rectangular pole is there, na? A rectangular pole is there. This is a pole.
Yes, sir.
How to find the polarity? By applying the thumb rule. Thumb rule what indicates? Right hand thumb rule.
Enclosed fingers.
Right hand thumb rule. Right hand thumb rule. Curled fingers indicates current direction. Thumb indicates flux direction. Current is inwards.
Yes,
are you seeing my face? See, current is inwards, current is outwards. It is coming inwards into outwards. Therefore, it will give the flux in this direction. Here it will give the flux in this direction. That's the reason it is north pole. And it is receiving the flux. It acts as a south pole. So we are finding the pole. Examiner simply is giving cross data. Is checking whether student is having idea about application of the right hand thumb rule. Curled fingers. Wrapped fingers are curled finger indicates current direction. Thumb indicates flux direction. Okay?
Sir, I did not understand.
So for example, can you tell me? I am giving cross and dot here on the field current. What is the polarity of this pole? How can you find?
Okay, sir. And dot means coming towards.
Cross means inwards.
Sir.
Fingers you have to wrap.
Enter into the paper. Cross means into the paper. Dot means outwards the paper.
Yes. And in which direction thumb shows? Upwards.
Yes, sir.
This is acting as an north pole. Same thing you apply for this. In this diagram also same thing you apply. How you will get? Current inwards. Cross means into the paper. Into the paper. The arrow is going into the paper. Inwards, outwards. Your thumb will be pointing right side, no?
Yes, sir.
Thumb will be pointing right side. And that is giving the flux, no? It is giving the flux. Flux direction it is giving like
Yes,
this.
sir.
Flux it is giving. Flux giving means north pole. But whereas it is receiving the flux. Receiving. I am not assuming. That is only the question mainly. You have to find the poles. Poles are given. Question is normal. Okay.
Okay, sir. Okay.
Right.
Sir, if we apply at South Pole side, sir.
South pole also. South pole also same thing. But flux in which direction? Flux is left to right only.
Okay, sir. Yes, sir.
Correct or not?
Yes, sir. Because it's
Always
left to
here.
right side.
Left to right it is going.
Yes, sir.
Flux is coming out from the north pole, coming receiving by the south pole.
Yes, sir.
Okay.
Sir, one more doubt, general doubt, sir.
Tell me.
Sir, roughly how many classes will go on for this synchronous mission, sir?
Roughly means as per allotted hours, if it is physical classes, it will be 55 hours, 50 to 55 hours. For hardly for you people, it may be 55 IES people, IES students.
Okay.
It is around 55 clock hours. So you mean to complete quickly, say what we need to do is we need to do some less number of problems. Okay, you are interested to complete. You mean to say complete quickly?
No, sir. No, sir.
No problem.
Roughly, I mean 15 classes or 20 classes. According like that, I want to plan another subject to study.
Yes. It is nearly maximum 60 hours you take. 60 hours means it is a matter of 15 days. Almost we take 15 days.
Okay, thank you, sir. Because only 3 months left, na, sir.
Yes. Yeah.
If possible, sir, if possible, if you require, please continue up to the 9:30 or more, sir.
Okay. No problem. I will continue.
Okay, sir.
5:30 to 9:30 I will continue. No problem.
Thank you, sir.
I will do it. I will try to complete quickly. If you are interested, say if you stay up to 9:30, I will be very happy.
Yes, sir. We are ready, sir.
Fine. So then I will continue up to 9:30. Nothing to worry. So let us complete quickly. Okay. Next. Hello. Unmute and you can ask.
Hello. Good evening, sir.
Yes.
Sir, can you please explain that 4 cases? Something?
4 cases?
Sir, I didn't get that 4 cases.
4 cases means when conductor is rotating. What is the right hand rule says? 4-finger flux, thumb shows motion of the conductor. When conductor is rotating, no assumption is required because you can point your thumb in the direction of motion. So when conductor is rotating, no assumption is required. Conductor clockwise rotating, you need to consider clockwise only. Counterclockwise, the counterclockwise. Case 1, that is. Case 2, if conductor is stationary, say. When conductor stationary, 4-finger flux direction, thumb motion of the conductor. You should know thumb direction, but conductor is not moving. Then thumb also not moving. But without knowing thumb direction, how can you find current? So what you have to do? Conductor is, you have to assume compulsory, one particular direction. It is not moving stationary, but you have to assume in one direction. Which direction you have to assume? Opposite to the field rotation. If field is clockwise, say, conductor is assumed to be rotating in counterclockwise. Actually, it is not moving, but you have to assume counterclockwise. The relative motion is increasing order, you have to assume. Opposite. Same direction, if you assume relative motion may be 0, na? That is wrong, but assume opposite. And third case, if both conductor is rotating, flux is rotating, but there is relative motion is there. Correct? One is 15, one is 400 RPM, relative motion is there. Then flux cutting action takes place. But when both rotating in the same direction, conductor is slower, you have to assume opposite.
Okay, sir.
Conductor faster, no assumption.
Okay.
Like that last case is, if both originally rotating opposite direction, no assumption is required.
No.
Relative motion already increasing. Okay.
Okay, sir. Okay,
Yes.
sir. Thank you.
Right. Yeah. Next, Sai Charan.
Hello, sir.
Hello. Yeah, tell me.
Sir, in case of two phase, in that you told that 1 and 1 dash and 2 and 2 dash, they are physically placed or for the analyzation we took like that, sir.
No. He has given the diagram. It is circular shape. You are asking about this question. No? You are asking about this question. Correct?
Not in question, sir. In our explanation, sir.
Yeah. In our explanation, poles are this. You are asking related to this question or some other question?
I am asking generally, sir. We will assume like that, no, sir. 1 and 1 dash.
Yeah.
They
Assumption.
are not. Okay.
This is only assumption.
But they are not physically placed like that, sir. In that armature.
Yes. They are not physically placed, but it is a general discussion. Relative motion is exist. If conductors are faster, slower. In that case, we need to assume like this one.
Okay.
You may be talking about. I understood this type of cases. You are.
Sir, in the explanation, sir. First starting.
First starting in the sense.
Yes, sir. In this one.
In this one,
Before
you
one,
have
sir.
given diagram. This is a see. Can be able to see. This is the machine. Say this is circle machine. It is not rotating. It is with some support. It is kept fixed. But in this conductor, I am keeping C1 dash, C2 dash, but it is not rotating. If you take the poles is rotating. Relative motion is there, induced EMF. But practically, machine never be like that. Practically, machine will be, rotor will be inside, stator is outside actually. But he is taking as a circle, that is making as a stator, stationary. Poles are rotating outside. Practical machines, poles will be inside actually. Poles will be inside and conductors are outside. Stator conductors. The poles are rotating means we'll keep inside actually. But he just want to confuse. He want to create some new question, no? New question. So therefore, generally students by seeing that question, they can understand. Rotor is a circle means he will assume like a rotor. No. Stationary armature carrying the two coils he has given. Okay.
Okay, sir. In that EMF waveform, sir, in two phase alternator. In this EMF waveform, I was confused in that when why we took both of E1 and E1 dash at the same place and we.
Not same place. I am taking only in one conductor one say.
So both of them become a coil and the current direction will be like clockwise or anti-clockwise in that.
Yeah, in two sides of the coil, EMFs are aiding only. If you take only one conductor, say, that will be how much? 10 volts peak. Both are together taken coil, it will be 20 volts peak. But in coil 1 dash, 2 dash, same. You treat it is like a coil. Or if you are interested only in one conductor, say that is E in 1, E in 2. No problem.
Okay, sir. If we say that it is a turn, then one will be a conductor, single conductor, and 1 dash will be a single conductor.
Yes, but both are said to be aiding, na? Both are aiding only.
Yes, sir. Yes, sir.
Their EMFs are not in phase opposition, in phase. Aiding.
Okay, sir.
Aiding. If you take one 10 volts, say 1 dash, another 10 volts, both together, if you take it is 20 volts, but 20 volts will be in same phase.
Okay, sir.
Okay. Wave shape.
Understood, sir. Yes, sir.
Okay. Right. Next. Anil. Tulasi.
Hello, sir.
Okay. Hello.
Hello, sir. Sir, how want to take the magnetic field direction, sir? Like in page number, last question.
Last question.
Question, sir.
This one? This one?
No, sir. Before page. No, sir. In question. Yes, sir. Here only, sir. In next.
You take flux is coming out from the north pole. This is north pole, say.
Okay, sir.
This is north pole, say.
Okay.
Flux is in this direction. It will goes to South Pole. Somewhere South Pole is there.
Okay, sir.
For example, South Pole is here. This is South Pole. Say how flux will come? Flux will come north to south.
Okay.
North to south.
If the conductor is at the side of South Pole also, we want to take the upward direction, sir.
Upwards. Exactly. Upwards only.
Okay, sir.
Upwards only.
Okay, sir.
Yeah.
Sir, in real life, like how we give the double excitation, sir, AC excitation, DC excitation.
That we will see later. Synchronous motor.
Okay, sir.
Stator excited with AC, rotor is excited with DC.
Yes, sir.
Rotor. For synchronous machine, we are giving stator side, any excitation will be there. Stator is excited,
Yes, sir.
is excited with armature currents, stator conductors.
Okay.
But rotor is
Okay.
extra, we are exciting. Induction motor is there, rotor, there is, from rotor side, there is no excitation. Is singly, only stator is excited. But here,
Yes, sir.
stator is excited, rotor is also excited. The topics again we will see at the end. These
Yes, sir.
points is keep on coming. Okay, after construction,
Okay, sir.
you can understand. Okay, next. Hello.
Okay.
Who is there? Anil Kumar.
Good evening, sir.
Yeah.
Hello, sir.
Good evening. You can unmute and you can ask. Okay. Hello.
Sir, 15F, sir. 15F.
Yeah. Hello. Tell me.
Sir, 15F, sir.
15F.
Yes, sir.
Page number 15.
Yes, sir.
Yes.
So in this second case, sir, conductor speed is more in poles. How to mark the dot, sir? I did not get that point.
No assumption is required. Flux is upwards, na? North pole.
Yes,
it is north pole. Therefore, flux is coming upwards only.
Yes, sir.
Okay.
Yes, sir. Okay,
Apply
sir.
your right hand rule. North pole.
Yes, sir.
Motion of conductor clockwise only. It is moving clockwise. And your finger must be in this tangentially. Right side.
Okay, sir.
Then current is outwards.
Outwards. Okay, sir.
Okay.
Sir, in this we have no assumption means we have take cross also, sir.
Where?
Sir, second case, sir, that the EMF in A is dot marking, no, sir, that point.
Yes, that. And you are expecting how it is cross?
Sir, that point only I did not get, sir. The flux is moving upward. Conductor also moving same direction, sir.
Yes. Then the
Okay, sir,
first
okay.
diagram and second diagram difference is first diagram also conductor is moving clockwise. But
Okay,
conductor is slower. Conductor is 1400 RPM. Pole is 1500. When
Okay.
conductor is slower, then you need to assume opposite.
Opposite.
Counterclockwise. But here already conductor is faster means no assumption is required. That's what I have written in the statements also.
Okay, sir.
Okay, right.
Okay. Sir, so we will derive that derivation of frequency, sir. In that you have told that one point based on the poles number of cycles that off, sir. Could you explain that point again?
Each pole will generate one half cycles. No?
Yes, sir. Yes, sir.
Each pole generate one half cycle.
Okay, sir.
When conductor is going, I am taking only one conductor. That conductor only I am rotating. Don't think not four conductors. Same conductor is coming to here. Same conductor is coming to here.
Yes, sir.
When conductor is at first position 0, second position maximum, third position 0.
Zero.
When conductor is going under north pole, it is generating positive half cycle.
Yes, sir. Positive.
When same thing is going under south pole, it is negative half cycle.
Okay, sir.
The two pole machine within one rotation, how many half cycles? 2 half cycles.
2 obstacles.
In other words, each pole generate one half cycle. That's all.
Okay, sir.
Each pole generate one half cycle.
1 obstacle.
The P poles are there, P half cycles, P by 2 full cycles. Okay. The next,
Thank you, sir.
Avinash.
Hello, sir.
Hello. Yeah, tell me, ma.
Hello, sir. One last dot, sir. In page number 8F, sir.
Page number 8. Tell me.
Sir, here one conductor is exactly under the north pole, no, sir. We want to have the maximum EMF, no, sir.
Yes, yes, yes. In one maximum.
While drawing the graph, we are
Maximum means this is it. This is
while drawing the graph, we are starting.
okay. that instant is this will be the instant. This is going to be that instant. I am drawing maximum voltage, na? But I cannot take entire so many points. Okay.
Okay.
But at this
Yes, sir.
instant maximum, until this is the instant where EMF is maximum, that is the at this instant.
Okay, sir.
I am taking that as a reference, therefore it is a sine wave exactly.
Oh.
Fine.
Okay,
Instead
sir.
of
Thank you.
taking different point by point, at that instant EMF is maximum. Only here you need to understand, in one first conductor EMF is maximum. After how much angle EMF is maximum in second conductor? After 90 degrees. Because pole will come after, pole is rotated 90 degrees. North pole will come under the second conductor. Therefore, maximum value of first conductor to maximum value of second conductor is 90 degrees. Why 90 degrees? Because conductor
Okay.
1 and 2, they kept at an angle of 90 degrees. Okay. Yeah.
Thank you, sir. Got it.
Hello, sir.
Hello. Tell me.
Sir, in a two-phase alternator, sir, we can take any other angle than 90 degrees, sir.
Two phase?
Alternator, sir.
Sir,
we can take, can we take, sir, any other angle than 90 degrees, sir?
No. Two phase machine compulsory, balanced winding 90 degrees only.
Sir, as in the three-phase machine, sir, we require a balance system so that we have assumed it 120 degree.
Yes, exactly.
So,
Two
sir,
phase is 120. 120. Two phase must be 90. Yes.
yes, sir. That was asking.
Ah.
Yeah. Any other compulsion is in there in two-phase alternator as like that also.
No. Because in two phase means phase difference is 90 means the rotating magnetic field will be produced and torque produced is maximum. When two MMFs are there, na, F1 and F2. Torque is proportional to F1 and F2 sine of the angle between both. Sine 90, na, maximum. So that's the reason two phase machines and two phase motors, they are kept at 90 degrees apart, phase 1, phase 2.
Sir, we can consider it like the split phasing principle. Split phasing phenomena we can relate with this, sir.
Yeah. Same as just like induction motor, how we are doing.
Yes,
Alternate also similar. It is a machine, AC machine, two phase, that is valid, everywhere valid.
yes,
90 degrees if you keep, then your rotating magnetic field will produce, RMF will produce.
yes.
Motor say torque will be produced. Even generator also torque is required.
Okay, sir.
Fine.
Sir, one more doubt, sir. Sir, in a phasor diagram you have drawn, in that, sir, you have considered the phasor directions are in anti-clockwise, sir.
Yes.
Sir, why we have not taken it in clockwise? Means when we have to take in clockwise?
If you take clockwise, see, in this diagram only, in this clockwise, if you take clockwise means which is leading, which is lagging?
E1 1 dash will be leading, sir.
No, lagging.
Yes, sir.
Counter lagging. But in this, in which phase EMF is first maximum? 1.
1. Yes, sir.
2 is after some time lagging. Lagging means the 2 must be lags because it is coming later. This waveform you see, actually omega t is the time axis, na?
Yes, sir.
Time axis. Therefore, first maximum is E1, second maximum E2, 2 dash. So if I write this is sine omega t, this will be sine omega t minus 90 because 90 degrees later it is coming.
Yes, sir.
So the phasors will be, this is only correct. If you take clockwise, what will happen? E11 dash will lags.
Yes,
Okay, maximum value of EMF will comes after 90 degrees later of 2 dash.
Okay, sir.
But it's not later, no? It is coming first. So 1 will lead, 2 will lags. After some time it is coming. Okay.
Sir, in three-phase waveform, a similar relation we can use, sir.
Exactly. That is what tomorrow I am going to take phase sequence, separate topic, 1 hour topic it is. This only I will write. First phase sequence means the order at which maximum values of induced EMFs obtained. Order at which maximum. Okay?
Okay, sir.
Yeah, fine.
And sir, in the fourth case, of sir, conductor is faster in field than field.
Huh?
Sir, the conductor is faster than field. The fourth case we have taken.
No assumption is required. Whether faster, slower, also no assumption is required.
No, sir, we have considered dot there. Then means why we have assumed that.
Yeah, dot only, not consider. I have given the solution finally. First question is
Yes.
written, and after that I am giving what is the answer. For that I have given. This one, na?
Yes, sir. Yes, sir. This case.
First question is given. This is the question for that. For case 3. This is case 4. Yeah. The first I am taking question is with black color, solution is with red color I have given.
Yes, sir. Sir, here we have assumed in first case cross, sir, and in second case dot, sir. But why, sir, we have assumed dot? That's I am asking.
See, just a minute. I am not assuming actually. This is your question. See.
Yes.
This is your question is like this. This is the question. That's the reason earlier also I have written question and separately solution is given separate. See, your question is, this is the question. Okay, this is your question, that's all. Tell me what is the answer now. I have not assumed.
Okay. Sir.
This is the question.
Okay, sir.
For that, what to do? Now, if you, while you are doing solution, you have to assume, na? Now I am doing first one. North pole is a conductor, na?
Yes.
When it is moving 1500, this is 1400, but you have to assume in opposite direction.
Okay, sir.
Because it is slower. Third case, it is third case. You need to assume in this direction. You have to assume in opposite direction, correct?
Yes, sir.
No, this one or I have given. Your doubt is this question or next question?
No, sir, that we are expecting that.
This only, na?
Yes, sir. Yes. Yes.
For this only, this is the question actually. This is the question, case 3.
Okay, sir.
This is the question. Now this is the solution. What is the solution for that? You have to assume in opposite direction, no? Therefore, what it will give? Cross. Cross. The cross I am finding, solution I am finding. I am applying my right hand rule, with that it gave cross. Second one, it will give dot. So this will give cross, this will give dot. You need to assume.
Yes, sir.
Okay?
Yes, sir.
Fine.
Thank you.
Hello, sir.
Ah.
Sir, can you take that first slide today? The first slide today.
Ah.
2 north poles with that 1 coil case.
This one,
This one or the coil one? Like, my doubt is that like the
okay.
induced, like, can we show that the induced EMF for the current due to that opposes the cause here?
Sorry.
Like, sir, the induced current should oppose the cause, right? So Lenz's law, like, can we say that? Can we show that it applies here? How it opposes that motion?
Yeah, tell me. Now I can't able to examine myself.
Sir, should I ask the question once more? Hello, sir.
Okay, anyhow, tomorrow I will explain.
Okay, okay.
Actually, okay.
Okay.
Any doubts are there? Tomorrow I can explain. I will stop here because now it is sound is starting. The people came to hear. Okay.
Okay, sir. Sure.
Stop here.